Good morning and welcome to part 3 of our course. We are officially halfway. Very exciting. Let's see where we are. Okay, I'm ready. So, the next portion, the next part 3, is really all about the integers. We've now taken a tour through other number systems to better understand our decimal system and addition, multiplication, subtraction in that number system, how we usually do it on paper, right to left. Now we want to just get, or rather develop and make sure that we have sufficient number sense. Some people might have a good number sense already, and some people might need a refresher. By looking at our first topic called divisibility, as well as those that follow, we are going to just explore our integers a little bit. So we'll mainly focus on the positive integers, 0, 1, 2, 3, 4, 5, and so on. Although 0, I guess, is both. Just the whole numbers. Some people call them whole numbers. That's not really the official term, integers. And we'll mainly focus on the one arithmetic operation that we haven't really given enough attention, which is division. So what do we mean by divisibility? First, we have an exercise that helps us answer that question. Let me get the book here. This one, like so. There we go. Exercise 9.1. Explore how 15 can be built multiplicatively from 5 and then 2. Now, what do I mean by that? Really, I can break 15 up into smaller pieces that are multiplied together to make 15. So it depends then what pieces, what smaller numbers I want to use. If I want to use a 5, well, then it's going to take 3 groups of 5. So 15 can be seen as being built out of 3 and 5. If I want to use, like in B, 2, I can say, well, I can use 7 2's to get as close as I can. Remember, everything here is just integers, no decimals or fractions or anything. That is going to get me to 14. I'm going to have to add one more to actually get to 15. So where 5 is used in a very clean way, that it perfectly fits in to 15, 2 doesn't work as well. I'm going to have a little bit of room between the 14 I can reach and the 15 that's my target. Okay, so the number of times we can fit in the desired number, we'll call that the quotient. And if there's any extra wiggle room, we'll call that the remainder. What's left after I've done what I can with the given number? So I have to have a number here. Now, how I do this is by way of division. We can see here that 15 divided by 5 is going to be 3. And we can say for this one in the bottom, 15 divided by 2 equals 7. with a remainder of 1. So the numbers in question here, we'll call them the divisors, because how we're going to get this breakup is by way of division. The division uh, operation is going to tell me all these pieces in how the original large number can be broken up. So now it's quite straightforward when I have these small numbers, but it's important to notice that given even large numbers, an A that's like the 15 and a B, we can always write A as being broken up according to B. Quotient times this B divisor, perhaps plus a remainder. The remainder could be 0, or it depends on what the numbers are. The remainder could be bigger. This remainder is always going to be between 0 and B. It has to be less than the divisor, otherwise I could have fit more B's in. So we write that as 0 less than or equal to R less than B. But if you see that and it feels a little bit intimidating, that just means mathematically that R is between, the remainder is between 0 and B, and it could equal 0. But it's not going to be uh, my divisor or too big, because then I could adjust it to have more B's fit in to my number. So all of these will look like this A equals Q times B plus R. So when the numbers are super small, well, there's not much issue. I can really just do it very quickly. But when the number is bigger, how do I find the Q? Let's say here, how to find Q and R in general. That is where we're going to use our long division method. Now, unfortunately, the division method being called long division is quite unfortunate, because kids hear the word long and they immediately know that this is going to be unpleasant. It's just the division. It's just division. I don't know why uh, really we have to call it long division, setting everyone up for a miserable time, because this is going to be long. It's not. It's just division. So get rid of that. Just division. And it's the same method that you're going to teach. We're not going to bother with doing this in Roman numbers and Babylonian numbers and all kinds of stuff. I have done it once. There isn't really a benefit to doing that in the division case. For some reason, I don't get the same benefit as I do in the other three. So we have exercise 9.2 giving us some larger numbers. And I want to find the quotient and remainder and split the large number up according to the divisor. So I have number 1. I have my A is 7,925, and my B, just to match it with what's in the box, is 7. So now I have to remember, how does this division work? Well, the large number is going to go into the house. I'm going to just give myself more space. Let's make it nice and big. People do division in a variety of ways. Stick to the detailed one. Stick to the detailed one. I don't care about all the shortcuts, synthetic division, all those fancy things making me feel that I'm amazing, yet I have no idea what I'm actually doing. That serves no purpose, because long division is not long. It is quite efficient. So what we're really doing here is we are dividing 7 into this number, but we're doing it in pieces. And different from the other three, we're doing it starting with the largest place value. So I'm going to go left to right. And it's really the only way it can work. So I'm just going to focus on the thousands digit and just say, how many times can 7 go into 7,000? Forget the others, just 7,000. Well, obviously, 1,000 times. Now, I'm not going to write the zeros here because those will get updated as I look at the other digits. But my 1 is in line with the 7,000 place. Well, maybe I can write it like this. Maybe that's better. 7 goes into 7,000 1,000 times. 1,000 times 7 is 7,000. So that shows how much of my original number is accounted for. I've used 7,000 already. So I want to subtract to see what I have left. And I have 925 left. So now I go to the hundreds place and see, okay, there are 900s. How many times does 7 go into 900? It's going to go into 900 100 times. So I'm just updating my answer. Not 100 more times 7 can fit. I've then used 100 times 7. I've used 700. So I need to take it away to see what is left. And there is 225 left. Now I've looked at the hundreds digit and fit as many 7s in terms of 100 times in as I can. So the next place I'm going to look at is the tens digit, and I have 22 tens left. So how many times does 7 go into 22 tens? It goes in, so I need to update this. It goes in 3 times, or 3 tens, or 30 times. So I update that, because 30 times 7 is going to be 210. Now I don't have to say 30, because it's, again, relative to the column that I'm in. If I say 3 times 7, it's really 3 tens times 7, so my answer is going to be 21 starting in the tens digit. So again, I have that luxury of just looking locally at the place, at the column that I'm in. That is what I've used, and I have 15 left. Now I have to go to the ones place. 7 goes into 15 2 times. I've then used 2 times 7, which is 14. And I need to take that away. Oh, just fits. And I have 1 left. And of course, 7 can't go into 1 in any whole number of times. So this allows me to say 7,925 is 1,132 groups of 7, if you will, plus 1 remainder left over. This is my quotient. This is my remainder. Okay, so hopefully everyone sort of remembers division. This first part is for me to practice because it's been left out in what I've done so far. So I need to remember the division method. I need to know what each step is doing, why it's doing it a certain way, what it's saying, what it's not saying. Everything we've done for addition, multiplication, subtraction, division has been left out a little bit. So feel free to interrupt me if you have any questions. I don't know how well you remember division. Oops. But hopefully you remember it perfectly. And if not, just practice some more. So we have our number 3,781 and our divisor is a 4. So again, we're not going to make the divisor big. It's just going to slow me down and not really do much in terms of my understanding. Once I can handle this, and I'm in grade maybe 5 one day, then I'll just brush up. Okay, what if this number is bigger? Is there any adjustments in how I say things? No, not really. Okay. So I set it up. In my house goes the big number, and then I divide by 4. So again, left to right, 4. So I'm looking at the thousands place first. 4 goes into 3,000 0 times. Now I'm not going to write the 0, but you can if you want to, but as a placeholder might not be the worst idea. But eventually in my answer, I won't start a number with a 0. But if you want to, go right ahead. Now you could technically say, my method says, then see how much I've used. 0 times 4 is just 0, so I haven't done anything. It's silly to just write stuff that doesn't do anything. So I need to then go to the next place, which is the tens, which means I look at 37 because it's 37 tens still left in my number. 4 goes into 37 9 times because 9 times 4 is 36. It's not really, right? But the method allows me to say that it's really 9 groups of 100 times 4 is 36 groups of 100. And to emphasize that, I don't think it's a bad idea to put zeros there and remind myself it's 900 times 4 is 3600, which I then take away. Many people don't write the zeros. I don't know if that's the best idea. Does it take me long to write a couple of zeros? Some people use lines or arrows. I don't know if that really encourages understanding what we're doing here. I don't want to take any shortcuts when it doesn't really save anything. It might just look strange to a student and they might think they see stuff that isn't really there. So what do I have left? I have 181. So obviously I've done the hundreds place. You see this digit is less than 4. I move on to the tens place, but then see it as 18 because I can't forget that one. 18 tens are left. 4 goes into 18 4 times, so I update the 0, which was really just a placeholder. 4 groups of 10 times 4, or 40 times 4, is of course 160. And I have 21 left. Then I go to the ones position, and I have 21 ones. 4 goes into 21 5 times. 5 times 4 is 20. That's what's used. And again, I have 1 left. The remainder could be 0, 1, 2, or 3. It's just not going to be 4 because then I didn't do my division right. So my original number of 7,381 can be split up according to 4 into 945 groups of 4 and a little remainder of 1. All right. We have one more just to see if there are any questions. You need to decide for yourself how much practice we need. We are not in a hurry. We can ask questions if there are any questions. Decide for yourself. I need to go practice this. And you can, of course, always check sort of on a calculator to find the quotient at least. So 6,415 inside my house. I divide by 6, left to right. So thousands first. 6 goes into 6,000 1,000 times. I like these zeros here. 1,000 times 6 is 6,000. So it takes care of that digit completely. And I have 415 left. Clearly now I'm in the hundreds column. Maybe I'll erase that to remind myself where I am. Maybe little arrows at the top. whatever works. And so I have 400. 400s left. 6 goes into 400s 0 times. I've used nothing, and that's why I can move on to the next one. I do have to look at it. Then I'm in the tens column. I see I have 41 tens left. To fit some 6s in, divide 6 into 41, I can get 6 of them. 6 times 6 is 36. It's not really 36, right? It's 6 groups of 10 times 6 is 36 groups of 10, and therefore 360. That I take away, I have 55 left. Now I move on to my ones column. 6 goes into 55 9 times. 9 times 6 is 54. That's all I can use. I have 1 left. Remainder is 1 again. Now it's just coincidence that for all of these the remainder seems to be 1. The remainder can be different, of course, but it's always going to be less than the divisor. So my original numbers, 6415, can be broken up according to 6 as 1069 groups of 6 plus 1. So we see for all of these, they didn't really fit in very cleanly into the given number. In that there were always a little bit left. There was always a little remainder. So let's just go back to my first example, splitting 15 according to 5, splitting 15 according to 2, and we saw sometimes there's going to be a remainder, and sometimes the divisor is going to fit perfectly, and no remainder. So no remainder. Well, that's not really true. It's a 0 remainder. There's always a remainder, but it could be 0. And then here there is, let's say here has a remainder, not 0. Let's say it like that. Either 0 or not 0. When, so let's say it like with regards to the 15 and so on. In the case where there is a 0 remainder, or we can say casually no remainder, that's okay. No remainder, we say that 15 is divisible by 5. When I do the division, there is nothing left over. 5 fits into 15 perfectly, in this case 3 groups of 5. When it has a remainder, has a non-zero remainder, I don't know necessarily what it is, it doesn't have to be 1, then we say 15 is not divisible by 2 in that case. So the concept of divisibility is really connected to what remainder do I get when I do my division. Okay. So in general, I don't know what numbers I'm going to have. I'm going to have my large A and my B. We say A is divisible by B if, oopsie, if my remainder is 0 when I write it according to my long division quotient remainder. So I do the division, I find the quotient, I find the remainder, If that remainder is 0, then we say A is divisible by B. And we can also write that in a short way, which is unfortunately a little backwards. B with a line and then A. So if you want the symbolic form, sort of in the mathematical language, it has this long line, longer than the height of the letters. It's my divisibility symbol. Divisibility symbol. But when I write it in this form, the small number comes first, so to speak. The divisor comes first in this mathematical sentence. And because of that, I like to casually say or read this to remind myself it's small, and then the divisibility symbol, then the large number, even though the sentence A is divisible by B, the large number comes first, and then the small one. It's flipped around. So I like to casually read this as B fits or divides into A, implying that it cleanly fits in. There's no remainder. So when I say that sentence, it's in the same order as the mathematical sentence. And then I don't get confused which one goes where, because I see people flip them around, which is not ideal, because it would then mean different things. So I actually like the informal sentence, and I'm going to use it often. B fits into A, or B divides into A, implying that there's no remainder. And that then helps me remember how to write it with the divisibility symbol, because then it's in line with how I say things. Now, if I think back about to my 15.5 example, I now have a divisibility. For example, we could say many things here now, right? We could say 15 is divisible by 5. That's one way. We could say, I like to say it casually, there's no confusion in doing that. 5 divides into 15, implying then with no remainder. But we won't say it if there is a remainder. We won't say it like that. So when we say 5 divides into 15, it implies that there's no remainder. So that's okay to say that. Mathematically, 5 divisibility symbol 15. Divisor comes first in that sentence. Don't flip it around. I can also say that by way of the quotient version, 15 equals 3 times 5 plus 0, of course. Then two important ones, which people seem to not be as familiar with as I would hope. The words factors and multiples. When I look at 15 and 5, I now have divisibility. They are called specific words. The larger number, I suppose, is called a multiple of the divisor. The divisor, 5 in this case, is called a factor of the larger number. So I want to be comfortable and very familiar with the words multiple and factor. Now they're going to come up a little bit more later once we have some more stuff discussed, but I want to mention it as early as possible so that there is no excuse when I use those words often. Okay. So multiple refers to the quote unquote bigger number. Think of a small example. Think of maybe you like 15 and 5. Numbers I have a good sense for. Don't make general statements when it feels a little bit detached. Using an A and a B, what are those numbers? Use a specific example to identify which of those pieces are named what and how do I say things and so on. The large one is a multiple of the small. The small is a factor rather of the large. Now, I don't want to I say casually for my own understanding large and small, but notice that they can be the same number. Let's take let's take 10. Take 10 as an example. Of course, I could take any number, right? Then I can say many things. If I divide 10 into itself, that's one group of 10 with no remainder. So 10 is divisible by itself. 10 divides into itself. Uh, 10 is a multiple of itself because 1 times 10 is 10. 10 is a factor of itself. Now I just took 10, right? It could be anything. It could be any number. I am not attached to this 10 in any way. I could just call it A or B or N for any number. Yeah, there we go. Make it an N. N, 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 N. So any number is a multiple of itself, is a factor of itself. So there's a little bit of an overlap. But when the numbers are different, sure, then I think of the big one being a multiple of the small one being a factor of the big one. The big one is divisible by the small one. The small one divides into the big one. But note that they don't have to be different, actually. They can be the exact same number. And these statements, can still be true. All right. So that is the introduction for divisibility. How do we feel about that? You decide. Do you feel good? Do you feel bad? Do you feel in the middle? It's totally up to you. But if you don't feel super comfortable, that just means you have to go practice a little bit more. So, next up, we have hopefully something fun. Divisibility. I have to sound this word out every time I say it. Divisibility tests. Now, what we want to do as part of our building of our number sense, just exploring these numbers and how some of them are easier than others and how they fit and relate to each other, all those things. We sort of develop that by this topic of divisibility tests. Now, in this topic, what we want to do is we want to have some knowledge when I look at a large number and I simply want to know. I have two numbers. I have a large number, much, much bigger than 15, and I have a small number, just single digit, for example. I just want to answer the divisibility question. Is the large number divisible by my small number? Yes or no? I don't want to go through the whole division process because that does get long then. Long division lives up to its name. I just want to know, if I were to divide the small number into the big one, do I get a remainder? Does it fit cleanly in? Is the big one a multiple? Is the small one a factor? And so on. Sometimes I just want the basic yes no question. I don't care what the quotient is. I don't care exactly what the remainder is. I just want to know if there is a remainder that's not zero. Just answer the divisibility question. And to that end, we have divisibility tests that allow us to just look at the large number and very quickly decide, yes, it's divisible, no, it's not. But of course, I need to know which divisor I'm interested in, right? So we're going to go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we'll stop at 12. So for each of these, we want to look at a large number and say, yes, it's divisible by 6, or no, it's not. Yes, it's divisible by 11, just very quickly, without doing the division and the whole long thing, which for large numbers is then going to be long. I want to just scan the number and see, yes, this number likes 2, this number does not like 7. How do I know? Now, we're not going to do these in order. We're going to go in increasing order of difficulty, starting with the easiest 10. So, first up, divisibility test for 10. Now, in the beginning, because we're starting with the easy ones and they're going to be very familiar, it seems quite unnecessary to actually write something out when it's so straightforward you almost don't even think about it anymore. But we'll quickly transition to ones that you maybe didn't know, or we don't really understand why the test is like that. You maybe haven't heard it before, but we started with the easy ones, and they can be quite straightforward. So I'm going to call well, just a number is, sometimes I want to call the number n or something. It depends on the test. A number is divisible by 10 if and only if the rightmost digit of the number is 0. Hopefully we all knew that one. That's how I see if it's a multiple of 10, if it ends in a 0. Now, I don't want to say the last digit because really it depends on which side you're looking at the number. I'll say the rightmost digit. For example, and again, we start at the very familiar case. 250 is divisible by 10. We can write 10 divisibility symbol 250. 253 is not divisible by 10. If you want to write that symbolically, you write the divisibility and then just put a line through it, strike through, to indicate not divisible. Do not write 250, then divisibility symbol, then 10. That doesn't mean the same thing anymore. The small one first, dividing into the bigger one, yes or no. Now, of course, this one's super straightforward. But when you look at the book, you'll see that I took a much more formal approach to it. Not because you have to know how to do that, but just to see, just because we're used to this for 10, the test for 10, doesn't make it obvious. Technically, and especially as we continue to the less obvious ones, you need to prove that regardless of the number that we take, whenever the last digit is a 0, that number will always be divisible by 10. And anytime the last digit is not a 0, it will definitely not be divisible by 10. If we go back to our inductive reasoning, I might take an inductive reasoning approach at an elementary school level, just giving examples. 250, yes, it works for 10. 253, no, it doesn't. Enough examples until little Timmy starts to draw a conclusion like, oh, it's only going to work if it ends in a 0. Let's explore that further. But that is not conclusive proof that I can take absolutely any number and this divisibility test is true. Inductive reasoning is not 100%. Now, I can guide the students by way of inductive reasoning because I might already know the true result. So it's perfectly safe and not going to lead them to an incorrect conclusion. But it's still, from their point of view, not conclusive that this necessarily works for any number. Any number. In order to be sure, I need to step away from specific examples and use deductive reasoning. So what I've done in the book is to show you what that would look like. Some proofs are short, some are longer, but they have a different look to them. As soon as I need to make a general argument and I'm not attached to the specific number like I can be in an example, it changes the look of how these things are done completely. Now, we don't need to worry about that because I'm not leading you to the wrong conclusions. But just know that to be 100% sure of all these tests are going to work always, it's a different situation. It doesn't look the same. Our purpose is to know the tests, have an idea of why they work, and by way of example is perfectly fine, and be able to apply them. So if you see things in the book that we did not specifically discuss or in the same way stated, don't worry about that. That means you don't have to know it for a test. It's really just to to see how things really look behind the scenes. All right, so I don't want there to be confusion between what I'm doing here and what you see in the book. It's not, the book is much more complete. I guess I was a little ambitious at that stage, and I thought, let's just show them everything. And if you ever see it a more difficult test and you want to know how could that be, how do I prove that for any number, it is in the book. So we did 10, right? Now we're just going to go through this list of numbers, and it's going to take as long as it takes. It doesn't matter. We'll pause, we'll stop when we need to, and we'll pick it up the next day and be done whenever we're done. The next one is going to be a 5. So I have my divisibility test for 5. Now let me show, before I go to 5, informally, why does this divisibility test for 10 work? We're used to it, so we don't question it. But if you hear it for the first time, some might say, well, why? When I have a number that ends in a 0, I can write it as a multiple of 10, which means it's divisible by 10. And when I have a number that doesn't end in 0, I can always, when I do my division, it's easy enough to see that the ones digit is going to be the remainder, and therefore make it not divisible by 10. Again, this is only an argument specific to this example, not a general proof. But for this simple case, it's usually enough to convince someone that, oh yeah, okay, it doesn't even matter what this 25 is, right? As long as I have a 0 digit there, I'm going to be able to write this, and therefore it's going to be able to be divisible by 10, and of course the other case not. So I have this if and only if situation, meaning I need both directions. That if I have a number that's divisible by 10, then the rightmost digit is 0. And if I have a rightmost digit 0, then the number is divisible by 10. So let's say this piece in the square bracket is equivalent to this piece in the round bracket. Sort of a technicality, but the if and only if means it goes in both directions. If I have one, then I necessarily have the other one. If I just had the if, then it's really only a one direction. Like if it rains, then the grass is wet. That only goes in one direction. I need the other side to indicate that they are equivalent in both directions, just as a side note. All right, just trying to think of all the things I need to say. A number is divisible by 5 if and only if, so I want the condition that is true always, no exceptions, if the rightmost digit is 0 or 5. Again, we all knew this. Let's move on with our lives. I'm not going to have an example for this one. It should be pretty obvious. And the further we go, the more elaborate the convincing may become. In the case of 5, I need to look at two cases, ending in a 0 or ending in a 5, and then show that I can split it up with no remainder in each case. And I also need to show that if there is another ones digit, regardless of what that is, it'll never work for 5. And examples don't necessarily show that. As I get more complicated tests, it's going to become less and less obvious. But these are fairly familiar, so I'm not going to spend too much time on it. This is our introduction. And we've done 5 as well. Next up is 2. Divisibility test for 2. A number is divisible by 2 if and only if. I'm just writing out these sentences, even for the simple ones or the familiar ones, just to be complete. If you're taking notes at the same time, then your notes are complete, so on. A number is divisible by 2 if and only if the rightmost digit is 0, 2, 4, 6, or 8. Of course, we all knew that. But it is tempting to say a number is divisible by 2 if it's even. That's not really correct, because what is even? A number is called even if it's divisible by 2. So if you think about this a little bit, if you say a number is divisible by 2 if and only if it's even, then you're not actually saying anything. It's like saying that's a dog because it's a dog. You're not really justifying why you're calling it a dog. For example, I just happen to be looking out the window and seeing a dog. You have to be more specific by referencing the actual properties of the number. And then you can say such a number is called even. And if it's not divisible by 2, it's called odd. But the concept of even and odd is defined according to divisibility by 2, which means you can't use that to explain what divisibility by 2 is, right? Then you're just looping back onto yourself, and you're not actually explaining anything. Technicality, but it's good to be aware of those things because I see people say that all the time. A number is divisible by 2 if it's even, but I don't know what even is if I don't have a confirmed understanding of divisibility by 2 first. So now you're just looping back on yourself, and it's not technically correct. So again, I have more options for my rightmost digit, which already makes the uh, convincing of someone, if I can say it like that, if you had to convince someone that for any of these cases, I'm going to be divisible by 2. I have more cases, more examples, more things to show to convince someone. Even though it is familiar, there's always someone to whom this is not familiar at all. And they are going to need convincing. How do I do that? Well, it gets the examples just need to be more varied to cover all the cases for each possible digit it can end with, and hopefully that's sufficient. But proof to show that it doesn't even matter what number it is. It could be anything beyond any example you could make, and it still will work, requires something a little bit more logically sound and complete, and those things are demonstrated in the book, just if you're interested. So we'll work our way through this slowly and increasing difficulty. And actually, I don't know why I wrote 12. We're not doing 12. But I'll say at the end, why not? We'll stop at 11, actually. No, get away from me, 12. Uh, we'll just take however much time we need and get through it whenever we get through it. So we're pausing here, and we'll pick it up with 4 tomorrow. Are there any questions before we end things here? All right, okay, thank you. Until tomorrow then.